Alright, now we'll do our second problem for the conservation of energy. Okay, so the problem is the volume flow rate through the pump shown is 0.014 meter cube per second, and the fluid being pumped is oil with a specific gravity of 0.86. Calculate the energy delivered by the pump to the oil per unit weight of the oil flowing in the system. Energy losses in the system are caused by the check valve and friction losses as the fluid flows through the piping. The magnitude of such losses has been determined to be 1.86 Newton meter per Newton. Okay, so the situation is that we have this pump right here, and we have an inlet point, and that's the point A, and the outlet point, that's point B. Now, the pump is actually a mechanical device that adds pressure to the system, and thereby it allows flowing of water, even the direction is opposite to that of the gravitational direction. Okay, so the flow of water is from A to B. And in the inlet, we have an 80 mm diameter pipe, and here for the outlet we have a 50 mm diameter pipe, so we have a smaller diameter for the exit, and here we have a check valve. Okay, so we have a pump, we have a check valve, and plus due to the length of the pipe we'll have friction losses. So the distance between point A and point B is 1 meter, and it says that the fluid is oil and the specific gravity is 0.86. Okay, so it says here that the energy losses are caused by the check valve and friction losses as the fluid flows through the piping. So but the problem also gives us the magnitude of the losses, which is it says here, which has been determined to be 1.86 Newton meter per Newton. Okay, so that's Newton per Newton meter per Newton, and that's just actually the same as 1.86 meters. Okay, so we have a pressurized system. We have pressure right here at point A and then point B. Okay, so for the solution, what we'll do is to establish first the energy equation. Okay, so the energy equation is from point A to point B is that we have a pressure head PA by the unit weight plus the elevation head plus the velocity head. Okay, so plus, since we have a pump, then we have an energy term, or H sub A is equal to all the energy that's going out from the system. So that's the pressure head at B plus the elevation head plus the velocity head at B over 2G plus we have actually H sub R, energy removed by mechanical, although this one is 0, plus H sub L. Okay, so let's try to cancel some terms here. So for the pressure, we have a pressure given, a gauge pressure of negative 28 kPa. And for the elevation, we have that, or that depends upon your reference line. Okay, and for the velocity, since we have the flow rate, for this is the flow rate, the volumetric flow rate. Since we have Q and we also have the diameter of the pipe, so we can actually solve for the velocity, because that's just the flow rate equation, which is the Q is equal to A times the velocity. Okay, so for the HA, that's that's the one we are solving for. And on the right hand side we have the pressure at P, that's given, and the elevation head is also given, and this is also given, and plus HR, this one is 0, and the HL is given. Okay, so therefore our equation is A sub A is just the pressure head difference, A, plus the elevation head difference, Z sub B minus Z sub A, plus the velocity head difference, V sub A squared, all over 2G, right, plus, okay, so our head loss, actually the head loss or the frictional losses through the along the pipe, which is H sub L, is 1.86. That's Newton meter per Newton. Okay, so let's leave it for a while and let's solve for V sub B and V sub A using the flow rate equation. Okay, so V sub B is equal to Q all over A sub B. Okay, so for the Q, that is 0.014 meter cube per second, and the area is, okay, so the diameter is 50 mm, and we have to convert this 50 mm into meters. 0.05 meters squared all over 4, and that's equal to 7.13 meters per second. So for the velocity at A, then of course we have the same flow rate, but we have different area. Okay, so 0.014 meter cube per second divided by pi times the diameter, which is 80 mm, 0.08 squared all over 4, and that's 2.79 meters per second. So therefore, substituting now the values to the above equation, so that's H sub A is P sub B, which is 296 kPa, 296 kPa minus, okay, this one is negative 28, minus negative 28 all over our specific weight, which is the specific gravity, 0.86 times the 9.81, that's the kilonewton per meter cube. Okay, so it is the pressure head plus the change in elevation, which is just simply 1 meter, right? Okay, plus the change in the velocity head, that's V sub B, right, 7.13 minus 2.79 divided by 2 times 9.81, and again this 9.81 is different from this one is the unit weight of water in kilonewtons per meter cube, whereas this one is the gravitational acceleration in meters per second squared. Okay, so plus the head loss, the given head loss of 1.86. Okay, so simplifying, we get 38.4 plus 1 meter plus 2.19 meters plus 1.86 meters, and we have 43.45 meters, or we can express it in terms of 43.45 Newton meter per Newton, which is just the same as this. Okay, so again, what we did in this problem is that we first establish the equation, the conservation of energy equation, and then we just cancel out, or we just remove any terms that's just zero. Okay, and in our case, in this problem, the HR is not present, so this one is zero, and this HA is what we're solving. The HL is given, so this will be our working equation. So we need to solve first for the velocity v sub b and v sub a, which we get its value when applying the flow rate equation, because we are given with the flow rate, the Q, right, the 0.14 plus the area, and therefore by using the flow rate equation, then we can solve for the velocity. Okay, so once we have the velocity, then we can substitute everything here in the equation, and then just make sure about the units. The units should be consistent, and we just add them up. I mean, algebraically add them up, so we get 43.45. all right, now we'll move on to our next topic, which is the conservation of momentum. All right, so for the conservation of momentum, basically it says that momentum is conserved. So that means that the momentum before is just equal to the momentum after. Okay. Momentum is conserved. Okay, so let's define, or let's review what is momentum. Momentum in the course of dynamics, recall that it's just simply the mass times the velocity, right? That's the definition of the momentum. And the unit of this is kilogram meters per second. Okay, so when we're talking about the conservation of momentum, we actually want to relate this conservation of momentum to, or the application of this is to find the forces, say forces induced by the fluids to its solid boundaries. Okay, so for example, the impeller of the turbines, or the vanes. Okay, so if we have this, let's say we have this rotating wheel or impeller, and we have the vanes right here, and we induce let's say fluid flow, right? So because of the fluid flow, this one can rotate, and that actually induces forces. Okay, so now let's define what is a force. Now, force is precisely defined as the change of momentum per unit time. This is the precise definition of the force, not this one. The definition of force is equal to ma, I think. Okay, so take note that this is just my opinion, and I've done research on this, and this one is actually this is the Newton's second law, right? And it's not actually written, it's not originally written or expressed in terms of this mathematical expressions, but rather it just says that the unbalanced forces, this one, it just says that the unbalanced forces produces accelerations. Okay, so if you have your solid body right here, and you have forces going to the right, F1, and you have forces going to the left, and yet F1 is greater than F2, and of course, where will this go? The direction is towards the right. Okay, so because of the unbalanced forces, then there's gonna be an acceleration in the body. Okay, so this Newton's second law is actually a statement of this one, so that's why it is a summation of forces that's acting on a body, whereas the precise definition of force would be coming from this mathematical expression, which is the change of momentum per change in time. Okay, so let's derive now if okay, so if we take the limit of delta t approaches 0, take the limit as delta t approaches 0, then this one would be actually dp all over dt. But what is p? Right? What is p? This is mv, right? mv all over dt. Okay, so since this is a product, then we can actually obtain two expressions. So if the mass is constant, then F is equal to m dv all over dt, and this is acceleration, right? The change of velocity. So this is ma. F is equal to ma. But if mass is variable but velocity is constant, no, velocity, yes, velocity is constant, then what we get is F is equal to v dm all over dt. And what is this? This is actually the mass flow rate. Okay, so and the mass flow rate, the symbol for this is m dot, and therefore m dot v. Right. Now, if we want to deal with the change of force, delta F is equal to m, then that's going to be changing, or the change in velocity. And what is m dot? What is this? What is the mass flow rate? Right? Isn't it equal to the density times the volumetric flow rate? Right? So m dot, the mass flow, is just equal to the density times the volumetric flow rate. So therefore, this will be equal to q, this rho times q times the delta v. Okay, so this will be the force exerted by the fluid, or exerted by the moving fluid to its solid boundaries. Okay, so now let's do a sample problem regarding this conservation of momentum. Okay, so the problem is a nozzle discharges a horizontal jet against a stationary vertical plate. The water flow rate is 0.03 meter cube per second, and the diameter of the nozzle tip is 30 mm. Find the horizontal force acting on the plate. Okay, so if we don't have any illustrations given, then I guess the first step to do is to draw the situation. Okay, so we have a nozzle right here, right, and there is a vertical, let's see, a vertical plate, a stationary vertical plate, and this nozzle is there's a jet of water flowing out from this nozzle. Okay, and it says here that the flow rate, right, the Q is 0.03 meter cube per second, and the diameter, this diameter, is equal to 30 mm. So this is a stationary plate. So the force, so solving now for the force, so F, or delta F, so if we have a force from, let's say, from 0, so it's just the same as F, it's rho Q times the change in velocity. Okay, so I guess we have to solve for, okay, so let's solve for the velocity first. Okay, so velocity would just simply be Q is equal to AV. Okay, so V is equal to, okay, so that's the velocity at this point, I guess. Okay, the area, so the area is just pi times 0.03 squared all over 4. I guess you should write first V is equal to Q all over area. So this one is 0.03 meter cube per second, and this one is pi times 0.03 squared all over 4. Therefore, our velocity is 42.4 meters per second. Okay, so since this is the given diameter, and of course, we can assume that the diameter all throughout this length would be uniform. However, the velocity here would be different. I mean, in terms of the vector, the vector, the vector form is simply because this one is purely horizontal. So if we write the x and y axis, and this one is purely x, and then at this point it will there's no more x, there's no more velocity on the x direction because it changes to the vertical direction. So along the x, then now we can write, or we can now solve for the force. So F is just equal to rho Q times delta V. So we have the mass density of water, 1000 kilogram per meter cube, times the volumetric flow rate, meter cube per second, times the change in velocity, which is simply the 42.4 meters per second, and we get the 1272 Newton. Okay, so this problem is just pretty straightforward. Okay, so we'll do another problem regarding this this momentum equation, but this time we'll be doing it in x and y direction. Okay, so for the next problem, the elbow is in a horizontal plane and is connected to two 4 inches scheduled 40 pipes carrying 3,000 liters per minute of water at 15 degrees C. The inlet pressure is 550 kPa. Find the forces exerted on the elbow. Okay, so we have an elbow right here, and there's an inlet water that's going to the right, and then of course, since this is a bend, then the exit will be going upward. Now, even though we are given in terms of the diameter and the thickness of the pipe, 4 inch schedule 40, and that's in English units, we are already saved from converting the units because we have the area right here, 8.21 times 10 to the negative 3 meters squared. Now we have a pressurized inlet. This is a closed conduit. So we have a pressurized here, pressurized point 550 kPa, and since this is just a small, let's say a small difference, let's say in the elevation or in the length, then this pressure would be actually would be the same as the pressure at at point 2. Okay, so for the solution, okay, let's draw first the free body diagram. The free body diagram. So we have here the elbow, and the forces that's acting would be we have a force, the pressure force, which is just equal to P1 times A1. Of course, since this is a pressure, then of course it's always perpendicular to to the surface. So that's P sub 2 A sub 2. However, we have also a force that goes together with this pressure force, and that's the force due to the motion. So we have a force here, force Fx, and since we have a flow that's going in this direction, then of course the force here would be upward. This will be our F sub y, and that would be the same provided that we have the same area. Okay, so if this is the same area, the cross section is the same, then this will be the same. Okay, and if we want to find the forces or the reaction, then we have a reaction along the x, let's say r sub x, and we have a reaction along the y, so that's r sub y. Let's label this as figure 1. Okay, so the second step is to solve for the flow rate, because we have here a given flow rate of 3,000 liters per minute, and we have to convert that to for Q, solve for Q, and we have to convert this in terms of meter cube per minute. Meter cube per second. So Q is equal to 3,000 liters per minute. Okay, times the conversion is 1 cubic meter per 1,000 liters, right? Times 1 minute per 60 seconds, and we have a 0.05 meter cube per second. Okay, so since we have the flow rate, then we can solve for the area. No, not the area, the velocity. Okay, so velocity is just equal to Q all over A, and our Q is 0.05 meter cube per seconds, and the area is 8, right? This one 8.21. Okay, that's actually 21.3213 times 10 to the negative 3 meters squared. That's 6.09 meters per second. Okay, so once we have the velocity, then we can solve for the force. Okay, so solving now for Rx, applying the equilibrium equation. Okay, so we will apply the equilibrium equation, which means that the summation of forces is equal to 0, because this is a steady, this is not in motion. So summation of forces x is equal to 0, and let's assume that forces that goes to the right are positive. All right, so we have here P1 A1 plus Fx, right, minus Rx. Okay, so we'll write here Fx plus P1 A1 minus Rx is equal to 0, and Rx is equal to Fx plus P1. Okay, so if we transpose this into the right hand side, what we get is Fx plus P1 A1. Okay, so I guess we'll continue this this problem in the next video.